The problem statement from GATE Physics 2021 paper reads as follows. As shown in the figure, two metal semiconductor junctions are formed between an n-type semiconductor S and a metal M. The work functions of S and M are phi S and phi M respectively, with phi M greater than phi S. And this is the diagram, this is the circuit that been given to us. M is the metal, S is the semiconductor, and M is again the metal. So it's MSM, metal semiconductor metal junction, with a specific bias voltage provided over here, right? And we have been asked the IV characteristics on linear scale. So on linear scale we have to see how do the IV characteristics of this specific device looks like. This is a multiple choice question with only one correct answer, and we need to find the correct one. Before we get into this problem, let's first understand a bit about the metal semiconductor junction. So this is so on the screens you can see a metal semiconductor junction, metal on the left, n-type semiconductor on the right. Now two things can happen. Phi m is the work function, so we'll just see in a bit what do we mean by work function. And when phi m is less than phi, this means the work function of a metal is less than that of the semiconductor, an ohmic contact is formed. So you can see the phi m is the distance between some vacuum level to the Fermi level. This is the definition of the work function, and this is the work function of the semiconductor. You can clearly see that phi s is greater than phi m, and hence this contact will be an ohmic contact. The second case is that when phi m is greater than phi s, and the contact that we get in this case is called a Schottky contact, and which you can see here. So this is the phi m, and you can clearly see this is the phi s. So I'll denote phi s here. This is phi s, right? You can clearly see that phi m is greater than phi s. This chi is the electron affinity, Eg is the band gap, and Ec and Ev, as we know, are the conduction valence band respectively. Now when this kind of a junction is formed, this is known as a Schottky contact, and when these are not in contact, right, here as well as here, so when we bring them in contact, this type of junction, the bends bend, and this type of behavior is exhibited by an ohmic contact. Similarly, bends bend in case of an Schottky contact also. We'll be restricting ourselves to Schottky contact, so I'll elaborate a bit more on how this band bending actually happens, because this is critical to the behavior of a Schottky contact and the IV characteristics that will eventually determine, right? So this was the band diagram that was given to us. Now how, so currently as you can see, there's a finite gap between the two materials. So metal is not touching the semiconductor as of now. When these two will touch, two things should happen. The Fermi level should align. So I'm writing this now. Fermi level should be constant. Why? Because it has to be in equilibrium, otherwise the electrons will continue to flow. Note that this is an equilibrium condition and no bias, should be same, right? So this is the condition that we have to satisfy. And one more thing we can note, see there are some electrons here, right? And there are some states, empty states here just above the Fermi level of the metal. So when a contact is made, some electrons will flow here. So because every system will try to be in the lowermost energy state, some electrons will jump from here to here, and some realignments will happen. So we'll see that now. So what's going to happen now is that, so the way to do it is, we first draw the Fermi level as it vacuum level as it is, and we draw the Fermi level of metal. So this is all filled, this is metal. Now what you do is that you fix this point, the point of EC. You just fix this point here that we see, just fix this point here, and similarly you fix this point EV here. These points will not change. However, as we notice, the Fermi level should be the same after the contact is made. So Fermi level inside the semiconductor should be like this, correct? So this is the EF. And we also know that in the bulk, this region is called the bulk, this region, because it will have very little effect on the metal semiconductor, will not penetrate into the deep. And since this is an n-type semiconductor, so conduction band should be close to the Fermi level, something like this. Similarly, so since EC is here, so you can clearly see that EV will be somewhere here, right? And now we can simply join this line like this. like this. Band bending will happen, something like this, and you can clearly see, and this will also have to be joined. So you can clearly see a barrier has formed here. This is called the Schottky barrier. This was the vacuum level. So you can clearly see that this kind of, and yeah, so here it is the, these are all electrons here, right? This is the semiconductor. This is a semiconductor and semiconductor, right? So this is how the bends bend. So the electrons some have jumped, and you can clearly see there's a depletion region that has been formed here. And so it's this, in some ways it's similar to a p-n junction as far as depletion region is concerned. So this is what we get in terms of a Schottky contact, and this is what I have exhibited the diagram here. So you can see it's very similar. So this was the, obviously vacuum level will also bend something like this, and so this was, so chi remains here, and you can also see phi s will be here. Eg, obviously the band gap remains the same because that's not changed, and this is called the built-in potential, very similar because this is some depletion here, so very similar to the p-n junction that we had. And this is the depletion width, as you can see, xt. Phi b is this nothing but the Schottky barrier. This is what we had, this is what I had just explained it using this diagram. Now the next thing, once we have seen how a depletion region is formed and whatnot, next thing we are going to talk about is the biasing, because IV characteristics in the forward bias and reverse bias, we need to talk about this. So we can see on the left you have the zero bias. I told you, the when we do not have any bias, so you can see there is some finite Schottky barrier, and there is some depletion. Vd is, you can see the built-in potential, so to speak. However, if you forward bias it, so you can see just like in p-n junction, this barrier, now note that there is some barrier to the electrons cannot freely flow like from here to here, they have to jump, right? So but we can see if we apply some forward bias, the barrier is, so the electrons that are coming, they have to jump a little bit less by what amount, the amount that's bias is applied, Va. So electrons have to jump, so more electrons can now jump, and hence the current can increase. So you can see everything has been shifted by Va upwards. The built-in potential has been now decreased, Vd minus Va, so more current can flow. So we can see that, so this is just like what we had in a p-n junction. So when we forward bias it, so very low current will flow, and then after a certain point of time, huge amount of current will start to flow again. This is the I, and this is the V, right? So this is the forward bias, right? So this is the current, and after a certain time it will increase exponentially, something like that. However, on the other hand, if we reverse bias it, now the built-in potential will, so to this conduction band will go further down, right? And a very less amount of current will flow, which is again just like the p-n junction. So this is something like this. However, after a certain point, the device will break down and a huge amount of current will flow. So we call this V breakdown, and this is the, on the left is the reverse side, right? This is the forward. So this is just very similar to a p-n junction, right? And this is what is been, this is a comparative analysis of a Schottky and a p-n junction. You can see that the nature remains the same more or less, the exponential increase on the forward side and the breakdown on the reverse side. However, there are two key differences. The knee voltage is much smaller for a Schottky diode, as well as the breakdown voltage is much smaller. So these are the two things that you have to keep in mind, and the leakage current is also pretty high for a Schottky diode. Now coming back to the problem, the biasing is shown here. So here the metal is on the positive side and semiconductor on the negatives. So this is a forward bias junction. On the other hand, this junction, this Schottky junction, is reverse bias. So we just saw in the previous slide that the characteristics look something like this, right? So what we have is that, so let's say when this is, when this voltage is positive, V applied is positive, right? Let's say it's 5 volts or something. So this will be conducting forward bias. So this is the diode 1, so I can call it diode 1. So diode 1 is here. However, diode 2 will be conducting in the reverse bias side. It would have broken down, so huge amount of current can flow, right? Huge amount of current can flow. So whatever the current is being provided by the diode 1, or whichever is the restricting one, diode 2, some current will flow. So in the forward side, you see, we'll see the combined result would be something like this. However, if we applied V applied to be negative in the case 2, let's say this is negative, some the reverse will happen then. Now this will be in the forward bias condition and this will be in the reverse bias condition. So same thing will happen like this. The curve essentially will look very symmetric. That's the idea, because both of these diodes are identical, so the curve has to look symmetric. This is not symmetric, this is not symmetric, and we know that in the reverse bias the direction of current will flip because we have changed the polarity. So this is also not correct. So this is the only option, and we just obtain using, sorry, option A is the correct one, because on this side diode 1, so 1 is forward and 2 is reverse. However, on this side 2 is forward and 1 is reverse, and this is symmetric curve. So option A is the correct one. Thank you for listening.